Good morning, everyone. A very good morning. Shall we begin the session? Yeah, today's topic is today's topic is signals. What is a signal? That is any process, that is any command that is given to control flow for the software to cooperate to provide the fundamental low-level execution of the mechanism that is known as a signal that provides a high-level software form of the exceptional control as a unique signals. So whatever the data, whatever the signal we are using, that is known as a signal. Up to this point in our study of the exceptional control flow, we have seen some hardware and software that is cooperate to provide the fundamental low-level exception mechanism, and we will also see how the operating system using the exceptions or uses the exceptions, how to use the exceptions to support a form of the exceptional data flow that is often known as a process control switch. And in this section, we will study a high-level software form of the exceptional control flow known as a Unix signal that allows the processes that uses the processes how to control flow or how to use that signal that is provided in this section, that is high-level software form of the exceptional control flow that is available under this, and that is known as a Unix signal that also allows the processes and the kernel to interrupt with other processes. So whatever the process that I'm using that is used to control flow, that is used for the interrupt. Now, what is a signal? That is the exact definition is given over here. So the signal is a small message that notifies a process that an event of some time has occurred. Some type means some type of the event has occurred. In the sense, whatever the data that is using up, so that event will be occurred in the connection with the subtype, in connection with the root type that is available under this. So it is a small message that notifies a process that an event of some type has been occurred in the system. For example, if I'm talking about the figure 8.25, that notifies the 30 different signals or different types of signals that are supported on the Linux system. The typing man7 signal on the shell command gives the list. And each signal type corresponds to some type of or kind of system event, and low-level hardware exceptions are processed by the kernel exceptions handler and would not be used or not be visible to the user processes. And the signals also provide some mechanism for exposing the occurrence of such exceptions to user processes. For example, if a process attempts to divide by 0, then the kernel sends it as a signal-free signal, that is number 8, and if the process executes an illegal instruction, then the kernel sends out the sig-ill signal, that is number 4. And if a process makes an illegal memory reference, then the kernel sends its out signal SCGV signal, that's number 11. Other signals that correspond to high-level software event in the kernel or any other user processes that is defined. For example, if you type a control C, that is control C command is used at the same time while the process is running in the foreground. Then the kernel sends a fortnight or the end signal to the foreground process, that is a number 2. The sig-kill, that is a number 3, and when the child process terminates or stopped, then the kernel sends out a 6 signal or 6 child signal, that is number 17, to the process. Now, next is signal terminology. One is sending, one is receiving. There are two types of signals. So, kernel sends a signal to the destination process by updating one state in the context of a destination process, and the signal is delivered for one of the two reasons. First is kernel has detected a system event such as divide by 0 error or on the termination of a child process. A process has invoked the kill signal or kill function to explicitly request the kernel to send a signal to the destination process, and a process can also send a signal to itself, that is sending a signal. Next is receiving a signal. So a destination process receives a signal that is defined when it is forced by the kernel to react in some way or the other to be defined in other ways. So the next part is receiving a signal. So whenever the kernel sends or delivers a signal to the destination, it receives or it updates in the context of the destination process also. And the signal is delivered for one of the two reasons. One is kernel has detected a system event such as divide by 0. That means any exceptional event that occurs that divide by 0. anything that occurs on the termination of a child process. So a process is invoked, the kill function explicitly requires the kernel to send a signal to the destination process, and the process can then sends a signal to the itself. Then next is receiving a signal. So a destination process receives a signal when it is forced by the kernel to react in some way to the delivery of the signal. And the process can then either ignore to the signal, terminate, or catch the signal by executing a user level function known as a signal handler. Now this figure shows how or what is the main idea about the signal handler that is used over here, that available over here. And the signal has been sent by the receiver, or signal has been sent but not received is known as a pending signal. At any point in time, there can be one pending signal of a particular type, and if a process is not received, if a process has a pending signal of type K, for example, then it is not queued up, they are simply discarded, and the process can selectively block the receipt of a certain signals. And when a signal is blocked, then it can be delivered, but the resulting pending signal, whatever the resulting pending signal that is available, that can be of various certain signal. Whenever it is blocked, it can be delivered, it can be used, it can be unknown. But the resulting pending signal will not be received until the process unblocks the signal. So one is the pending, one is terminating, one is discarded. Now this is signal handling. This is signal received by the process. This is the control process to the signal handler. The signal handler runs, the signal returns to the next signal. So one is the signal received, then control, then runs, then signal returns, or handler returns to the next instruction. Yes, a pending signal is received at most once. So this is the maximum time there is a pending signal. If the pending signal at the 2 times or more than the 2 times, then it becomes converted into the detained signal. And for each process, the kernel maintains a set of the pending signals in the pending bit vector and the set of the blocked signal in the blocked bit vector. And the kernel also sets the bits K in pending whenever a signal receives, whenever a signal qualifies, whenever a signal of the type K is delivered, and clears the bit K in pending, whereas a signal of the type K is received. The next part is sending signals. So Unix system provides a number of the mechanisms that is available for sending the signals to the processors, and all of the mechanisms rely on the notion of a process group. Whatever the process group that is available, that process group may be in any of the function that is identified by the positive integer group ID, that is known as a process ID or the PID. That is the same that we have discussed. And by default, a child process belongs to the same process group as its parents, and the process can change the process group of itself or another process by using the set PGID function. And this is the set PGID function that is available over here, PIDT, PID, PIDT, PGID. Then returns 0 on success and -1 on the error. It is changing the process group of the processor's ID to the PGID, and if it is 0, then the PID of the current process is used. But if the PGID is equals to 0, then the PID of the process specified by the PID is also maintained, that is also used for the process ID or the process group ID. And for example, if the process 15213 is a calling process, then set PGID 00 creates a new process group whose process group ID is 15213 and adds the process 15213 to this new group. The next is sending signal with the bin kill program. So bin kill program sends an arbitrary signal to another process. For example, if I'm taking about the Unix bin kill -9 15213, that also signal or that also provide the signal sig kill to process 15213, and the negative PID causes the signal to be sent to be every process in process group PID. For example, yes, if I'm talking about the command Unix bin kill -n 15213, that sends a kill signal to every process in the process group 15213. I know that we use the complete path bin kill here because almost some Unix shells have their own built-in kill function. The next is sending the signals from the keyboard by using the abstraction of a job to represent the process that are created as a result of evaluating a single command line. At this point of time there is at most one foreground job and zero or the more background job. For example, typing Unix is sort creates a foreground job consisting of the two processes connected by the Unix type, one running the ls program, another running the sort program. And the shell also creates a separate process group for each job. Typically, the process group ID is taken from one of the parent processes in the job. For example, yes, this figure shows a cell with the one foreground color, one background color. The next one is how to send the signal using the kill function, that is how to delete the function, how to delete the signal. This is hash includes is type.h, signal.h, int kill, PIDT, PID, int sig. If PID is greater than 0, then the kill function sends the signal to the process PID. If it is less than 0, then the kill signal or the kill sends the signals to the every process in the process group absolute. And this also shows an example of a parent that uses the kill signal to send the save signal to the child. This is one of the program. It is responsible for PID.fork equals to 0. Then pause printf control never reaches over here. Then exit 0. Then kill PID signal kill. Exit 0. This sends a signal with the alarm function that is used with the alarm signal to itself by calling the alarm function. This is hash include unistd unsigned int alarm unsigned int. Yes, that is returns remaining section of the previous alarm or 0 or not or 0 if no previous alarm is used. That sends out the signal to be available with the data that sends out the signal to be available with the SIG alarm signal to the calling process in the 6 seconds. Now next part is receiving a signal that is available with the function that is a iNext for the next instruction. That have parameters like the default action, then process terminates and dump score. This is a program for the process termination. Hash include csapp.h. Then void handler. This is the static int beeps equals to 0, beep plus beep is less than 5, not equals to 5, less than 5. That means it runs 4 times 5. Yes, because it is less than 5, not equals to 5. This we have done yesterday. That the process stores by restarting or by restarted a sig called signal. Then process ignores a signal. And if the handler is sig ing, then the signal of the type is also ignored, or the signal of the type is also are also ignored. Then sig delete, then the action for the signal of the type signum also reverts to the default action. Otherwise, it will create a signal handler that is also executed, or that the handler of the or execution of the handler is also referred as a signal type or handling a signal. And when a process catches a signal of the type K, it process or the handler is told for the signal K is invoked with the signal or some integer argument to the value K. And this argument also allows the same handler function to catch different types of the signal that is available with the second signal that is available with the data type signal. And signal handler are yet another example that is available over here for the concurrency control in this. Next is signal handling issues. What are the signal handling issues are available? First is pending signals are blocked. So it automatically blocks. Yes. Whenever there is a pending signal, it automatically blocks out. Then pending signals are not queued up. If there are for example, if there are 4 pending signals, they are not queued up in this one. There is a one at least. Yes, there can be at most one pending signal of any particular type K, for example. The signal calls can also be interrupted. That also is told out a signal child or the CHLD handler then creates a 3 children, each of which runs for 1 second and terminates, and in the meantime the parent waits for a line of the input from the terminal and then process it. This is one of the example. This is a line X signal 1. It's hello from child 130 or 10320. Then hello from child 10321. Then 222022. This we have done. This is not in your syllabus. Next is non-local jump. So C provides a form of the user level exception control flow that is known as a non-local jump that transfers the control directly from one function to another function concurrently. That means at the same time it executes, at the same time it jumps from one location to another location, and then also use the call and return sequence that is used with the set JMP and the long JMP function.